Hello, my name is Eldad Levy, and I will talk about the thermal design of electronic systems. I am a co-owner of CIS Computerized Analysis and Simulation with more than 15 years of experience in the field. Specialized in consulting and simulation in thermal, dynamical, and mechanical field, especially in electronic packaging from die level up to data center size. The project and knowledge deal with the following markets: the telecom market, the datacom, military, medical, and a lot more. The main challenges of today electronic packagings are higher speed of the electronic component, smaller size and volumes, higher overall power of the system and the components, higher power densities at all levels, higher allowable temperature of the component at the system level, lower cost needed by the manufacturer and the customers, and higher reliability in order to withstand a lot of years. But the basics physics rule did not change. Those are the challenges we, the thermal engineer, are facing with. This slide we can show the microprocessor power dissipation trends. The graphs are old, but the trade is the same trades. We can see the power changing over the years, and the power is increasing every year. Today, 9010, we can see that the CPUs are 150 watts. The network processor are more than 100 watts. The InfiniBand processor are about 100 watts. And the FPGA are 50 to 60 watts. Those power in electronic cards give about 200 to 300 watts per electronic card in the current systems. System heat density trends. We can see that in the last years, the heat density is increasing every year. In those days, at data centers, we get more than 20 kilowatts per square meter, which is a lot of heat. Electronic packaging thermal issue and cooling channel can be found in all the scales, from microns to meter sizes. From the die level in the components, at all components like AC component, optic component, power component. Then we are arriving to the electronic cards, to the daughter board cards on the electronic cards, to electronic module, chassis of all kinds, from 1U up to 20U, then to the ODU, which mean outdoor units, racks, all of them up to data center, which you can see a figure of a thermal simulation of a data center in these slides. The coolant knowledge is starting from the basic phenomena, which is a conduction, convection, and radiation. It is increasing. We are getting to the forced convection cooling, which is fan and heat sinks. The thermal resistance issue is very important in order to reduce the temperature difference. And we are using the top-of-the-edge cooling methods, such as heat pipe, thermoelectric cooler, phase change material, water cooling system, and in all of them we need to use the top-of-the-edge numerical tools. In these slides, we can see a design that you don't want to make, and this is another one. And now we can talk about good design. A good design including using thermal knowledge and use of numerical tools. At the slide, we can see a telecom chassis. At the left side, we can see the design. At the right side, the simulation. This is a 3 kilowatt chassis, which was designed by numerical tool, which give us a very good thermal design. Here we can see another example, how to design electronic card. the electronic design at one side and the thermal simulation at the other side. And by using thermal simulation, you can choose the right component and give the best design needed. The today market needs thermal solution to most of the electronic systems. After the course, you will know to identify the thermal problem, to use simple calculation and rule for basic thermal simulation for the first phase, and to use more accurate and sophisticated calculation for the second phase, to identify the need and to use numerical tools. The most important, you will know how to design and solve the electronic system thermal issue. Thank you. Hope to see you in the course.
Okay, thank you.
Hope to see you in my course.